the Lebesgue integral already now Riemann integral part of the same concept, but it's a little bit different. Differ that is that depend on the partition on the intervals the partitions is the sets measurable set that is called that is the difference. So the f be a bounded function on a comma b. So capital M small m la define that is in the Riemann integral the capital M small m define and capital F that is depend on the partition இது வந்து இன்டர்வலா இருந்திருக்கும். இங்க வந்து measurable set இருக்கு. That is the different. So f be the bounded function on a comma b, e be the subset of a comma b. E be the subset of a comma b. Okay, and capital M of function f over e and small m capital F small m of the function f over e. How to define capital M is the supremum of the function f of x, and with respect to the set e, x is for every x belongs to e, and small m is the infimum of the function, and with respect to the set e. Okay. So instead of dividing the a comma b into the intervals, that is the Riemann integral intervals are divided பண்ணிருப்போம். We will partition the capital a comma b into the measurable subsets. Okay. Riemann integral intervals are divided பண்ணுவோம். இங்க subset are divide பண்றோம். That is the measurable subset are divide பண்ணுவோம். That is the difference between the Lebesgue integral and the Riemann integral. So அங்கேயும் capital M என்றது supremum தான், இங்கேயும் capital M என்றது supremum தான், small m என்றது அங்கேயும் infimum தான், இங்கேயும் infimum of the function தான். But அங்கே வந்து depend on the partition of the intervals, அந்த intervals பேஸ் பண்ணியிருக்கோம், இங்கே அதே subset பேஸ் பண்ணியிருக்கோம், that is the measurable subsets பேஸ் பண்ணியிருக்கோம். And measurable partitions, so how to define the measurable partitions of P of A comma B. So that is measurable partition P of A comma B, that is a finite collection E1, E2, En of measurable subsets of A comma B such that union of the Ek should be equivalent to A comma B. Did you understand? So அங்க வந்து intervals இருக்கும் I1, I2, I like that. இங்க வந்து E1, E2, En என்றது measurable subsets of A comma B. இது எல்லாத்தையும் யூனியன் பண்ணீங்கன்னா we get it the closed and bounded interval A comma B கிடைச்சிடும். That is the measurable partition P of A comma B. So and also each and every pair of the partitions, measurable partition, that is the measurable partition P, the intersection of the measure of Ej intersection Ek, and such that the measure of Ej intersection Ek should be equal to 0. For Jk equal to 1, 2 and so on n, J is not equal to k. ரெண்டு different partitionக்கு intersection எடுத்தீங்கன்னா, that is the measure of intersection should be equal to 0. The E1, the sets E1, E2, En is called the components of the P அப்படின்னு சொல்லுவோம். This is called the components of the partition P, measurable partition P. So E1, E2, En is the components of the partition P. Suppose PQ என்றது ரெண்டு measurable partitions, ரெண்டு measurable partition na, then Q is called the refinement of P. The Q is called the refinement of P if every component of Q is only contained in some component of P. So every component of the Q is ரெண்டு partition இருக்கும், measurable partition இருந்ததுன்னா, one is refinement of the other one na, அந்த one உடைய எல்லா componentம் complete P உடைய componentல இருந்ததுன்னா, some componentல இருந்தா, that is called the the partition Q is called the refinement of the P. That is, if the components of Q are obtained by breaking of the components of P. That is, if the components of Q are obtained by breaking of the components of P. Okay. Components of Q that is the components of P split பண்ணி கிடைக்கிறது. That is the idea. So the measurable partition P is a finite collection. Measurable partition P is a finite collection of the subsets. Collection of subsets whose union is all of A comma B and whose intersection with one another have measured 0. Yeah. So that is if sigma equal to x naught x1 xn is a subdivision of A comma B, that is in the Riemann integral, and the component intervals I1 I2 In, that is then I1 I2 In is a measurable partition of the A comma B. So there are the many measurable partition of A comma B whose components are not intervals. Suppose if E1 is the set of rationals in A comma B, E2 is the set of irrationals in A comma B, then E1 E2 is the measurable partition of A comma B. Did you understand? That is a very important idea. So that is the difference between the Riemann and the Lebesgue integral. So here when you choose the some intervals, how to choose the measurable partitions, that is the set of rationals and the set of irrationals of that collection. Then E1 E2 is called the union பண்ணீங்கன்னா that is the intervals of A comma B. Clear? So that is called the measurable partition of A comma B. So the how to define, அங்கேயும் upper sum lower sum define பண்ணப்போ இங்கேயும் upper sum lower sum define பண்ணணும். F be the bounded function. Okay. So the bounded function on A comma B. P is the partition, measurable partition of A comma B. How to define the upper sum for the function F over the partition P. So then summation of capital M F over Ek, that is the partition, one of the partition. So capital M of F over Ek into small m and Tk. அங்கே வந்து length போட்டிருப்போம், இங்கே வந்து measure போடுறோம். செட்டுக்கு வந்து லென்த்து போட முடியாது, செட்டுக்கு என்ன பண்ண முடியும், மெஷர் தான் போட முடியும். அதனால தான் மெஷரபிள் தியரி முன்னாடி பார்த்தோம். ஸோ மெஷர் ஆஃப் ஈகே, தட் இஸ் த டிஃப்ரென்ஸ். ஓகே, அங்கே வந்து லென்த் ஆஃப் த இன்டர்வல்னு போட்டிருப்போம், இங்கே மெஷர் ஆஃப் ஈகேன்னு போடுறோம். ஓகே, தட் இஸ் த டிஃப்ரென்ஸ் பிட்வீன் த அப்பர் சம் ஃபார் த Riemann and Lebesgue integral. So the same way we can define the lower sum. Lower sum into the small m of F over Ek into measure of Ek. Measure of Ek. That is the definition for the lower sum corresponding to the partition P. The summation of m of F over, that is means that's a infimum. Capital M is the supremum of the function. Small m is the infimum of the function. So if E1, E2, En are the component intervals of the subdivision sigma, and then upper sum and defined here, the precisely the same as upper sum of the F over sigma, the Riemann integral. The set of numbers upper sum F over sigma for all subdivision sigma is a subset of the set of numbers upper sum of F over P for all measurable partition of P. Okay, and இதே மாதிரி இல்லாமல் அங்கேயும் ஒன்று பார்த்துருப்போம். that is the F be the bounded function. Every upper sum for the F is greater than equal to every lower sum for F. That is the lemma. Upper sum is always greater than equal to lower sum of the function. If P and Q are any two measurable partition of A comma B, then upper sum of F over P is greater than equal to lower sum of F over Q. Okay. So infimum of the upper sum என்ன சொல்லலாம், that is upper sum is greater than equal to lower sum. So infimum of the upper sum is greater than equal to supremum of the lower sum. Supremum of the lower sum. So infimum and supremum taken overall measurable partition P of A comma B. So then, so the Lebesgue upper and define the Lebesgue upper and lower integrals of the bounded function f on A comma B. So on the Riemann integral define like that in the Lebesgue integral how to define Riemann integral is always integral A to B மேலே ஒரு bar போடும், that is the Riemann upper and lower integral. So the same way the Lebesgue and upper and lower integral define as Lebesgue upper and lower integral define as, that is f be a bounded function on A comma B. The Lebesgue upper integral L of integral A to B f of x dx equal to infimum of the upper sum. Okay, again this is the definition. So the same definition, but is here only the different by the measurable partition P of A comma B. The lower integral is defined as supremum of the lower sum. Supremum of the lower sum. So the Lebesgue integral is exist, no? Both are equal. Both are equal, then Lebesgue integral is exist. And that is very important. So the Riemann integral, Riemann lower integral of the f is always less than equal to Lebesgue lower integral, that is less than or equal to Lebesgue upper integral, that is less than or equal to Riemann upper integral. Okay, that is the relationship between the Riemann and the Lebesgue integral. And f is the bounded function on A comma B. F is the Lebesgue integrable on A comma B. Na? The Lebesgue upper and lower integral both are equal. Riemann is the same concept. Riemann lower and upper integral both are equal, na? Then Riemann integral is exist. The same idea here. So exist rendu both are equal are the just Lebesgue integral of integral A to B f undi. So f is the Lebesgue integrable on A comma B. Na? F is belongs to L of A comma B. Okay. And f be a bounded function on A comma B, and f is Riemann integrable on A comma B, then f is Lebesgue integrable on A comma B. Or bounded function function is the bounded function f is Riemann integrable obviously f is Lebesgue integrable. So that is Riemann integrable is equivalent to Lebesgue integrable. And f is bounded function, f is Lebesgue integrable on A comma B. If only if the for each epsilon greater than 0 there exists a measurable partition B of A comma B, the difference of the upper and lower sum is always less than epsilon. The same conditions are in the Riemann integrable also. Yeah. So upper sum less than lower sum plus epsilon, or difference of the upper and lower sum is always less than epsilon. For example, chi be the characteristic function of the irrational numbers. Characteristic function of irrational numbers in 0, 1. E1 is the set of irrational numbers in 0, 1. E2 is the set of rational numbers in 0, 1. So the P you can define the partition E1, E2 is the measurable partition of A, B. So chi is identically 1 on E1. E1 la 1 irukum. Yena chi is defined as the characteristic function of the irrational numbers. And chi is identically equal to 0. F 0, that is x belongs to E2 ஆறுதுனா ஏன்னா E2ன்றது ரேஷனல்ன்றதுனால அப்படின்னா கேப்லியம் என்ன வரும் கேப்லியம் and small m both are equal to கேப்லியம் is the supremum of the chi. Supremum of the chi is 1. Supremum of the chi is 1, and with respect to E1, with respect to the E1 partition E1 is 1. Small m ன்றது infimum of the chi with respect to infimum of the function chi of x with respect to E1. E1 is always 1. So, அதனால small m with respect to E1 1 தான். அதே capital M with respect to E2 na, that is 0, small m with respect to E2 na 0. So upper sum என்ன வரும்? Upper sum is the summation of capital M with respect to E1 and E2 into measure of E1 plus measure of E2 இல்லையா? So that is what is the definition? That is the summation capital M of lambda over E1 and into measure of E1. So plus capital M of lambda over E2 into measure of E2. So that means this is 1. Okay. So 1 into measure of E1, 0 into measure of E2. So that is equivalent to 1. Lower sum the same way defined. So that is 1. So upper sum, lower sum, it is implies equal, both are equal. So therefore that is lambda is belongs to Lebesgue integrable on 0, 1. Lambda belongs to Lebesgue integrable and of 0, 1. Okay. So that is integral of 0 to 1 that is a characteristic function is equal to 1. But the same type of problem அங்கேயும் பார்த்திருப்போம். The chi is not a Riemann integrable on 0, 1. The chi is not a Riemann integrable 0, 1. But here the chi is called the characteristic function chi is called that Lebesgue integrable on 0, 1. So that is a very important example for understanding of the Lebesgue integrable. So the most function f, there is no partition P for which upper sum and equal to lower sum. So the function that is lambda, okay, like I, that is the chi of the preceding, that is f is belongs to exception, is in the exception, that is f is belongs to Lebesgue integral of a comma b. The partition P is such that 1 holds, that is 1 means usually depends on epsilon, that is upper sum, the difference of the upper and lower sum is always less than epsilon. Okay. F is Lebesgue integral now, that is called the difference of upper and lower sum is always less than epsilon. That is every bounded measurable function f is Lebesgue integrable. That is a very important point. So the measurable function is the important role in the Lebesgue integrable. Okay. And f is bounded measurable function. If f is the bounded measurable function on a comma b, so then f is Lebesgue integrable on a comma b. F is Lebesgue integrable on a comma b. So that is here some examples. So let f of x equal to 2 for the 0 to 2, 0 to 1. F of x equal to 4 for the 1 to 2, f of x equal to 3 for 2 to 3, f of x equal to 2 and 3 to 4. So if sigma is the subdivision, that is called 0, 1, 2, 3, 4, f 0, 4. So calculate upper sum of f over sigma, upper sum of f over sigma. So then sigma equal to, that is 0, 1, 2 something, there is a partition of 0, 4. I1 into the 0, 1 and I2 into the 0, 1, 2, I3 into the 2, 3, I4 into 3, 4. So what you have to compute the capital M? Capital M is the supremum of the function on I1, I2 and I3 and I4. So on I1 pathina, that is the supremum is 0, 1, I1 into the 0, 1 illiya. So the f of x equal to, that is equal to 2. So therefore m of f over I1 under that is called the 2. I2 la வந்து பாத்தீங்கன்னா 1, 2 டிஃபைன் பண்ணிருக்காங்க. ஃபங்க்ஷன் ஆனா 4 தான். ஃபங்க்ஷன் f of x equal to 4 is always 4. So the capital M is 4. on I3 la pathina capital f of x equal to 3. So on I3 la pathina there is a capital M is 3. On I4 la pathina capital M is 2. F of x equal to 2 constant function. So length of the interval pathina first one uடைய length of the interval 1 minus 0 1. I2 uடைய length of the interval that is the 2, that is 2 minus 1 1. I3 உடைய length of the interval that is 1. I4 உடைய length of the interval 1. The upper sum பாத்தீங்கன்னா எல்லாத்தையும் ஆட் பண்ணுவோம் length of the interval பேஸ் பண்ணி. So that is we get it the result இல்லையா? ரீமான் இன்டெக்ரல் இதான் பார்த்துருப்போம். Okay, so upper sum பண்றது. Here k equal to 2 3 4, that is the 2 3 4. E2 E3 E4 னு அர்த்தம். So E2 E3 E4, that is Ek the inverse image under f, inverse image under f of k comma k plus 1, inverse image under f of k comma k plus 1. So show that partition P equal to E2 E3 E4 is a measurable partition of 0 comma 4, is a measurable partition of 0 comma 4 னு சொல்லணும். So for example இங்க பார்த்தீங்கன்னா E2 ன்றது inverse image, how to define the inverse image of f of k comma k plus 1. அப்படின்னா E2 னா ஒரு inverse image of the function f inverse of 2 comma 3 இல்லையா, 2 comma 3. 2 comma 3 னுடைய inverse image என்ன? The collection of the x எங்க இருக்கணும், டொமைன்ல இருக்கணும். That is the function உடைய domain is called the 0 comma 4. So x belongs to 0 comma 4. So what are the condition? That is the inverse image of this something. The f of x ன்றது 2 to 3 ல இருந்ததுன்னா அதனுடைய corresponding x ன்றது is belongs to the E2. அப்படி பார்த்தீங்கன்னா the f of x is 2 to 3 னா f of x ன்றது 2 எங்க இன்டர்வல்ல, on these intervals, and 2 is belongs to 2 comma 3. Okay, that is called that is a 0 comma 1 union 3 comma 4, 0 comma 1 union 3 comma 4. So for this function is defined. So that is for the 0 comma 1, that is the 2, and 3 comma 4 is also 2. 3 comma 4 is also 2. So the function is defined for that 2 comma 3 னுடைய inverse image, that is called 2 to 3, 2 less than or equal to f of x. f of x ன்றது 2 ஆ இருக்கணும், and f of x ன்றது 3 குள்ள இருந்ததுன்னா அதனுடைய corresponding x எல்லாம் belongs to the something. So அப்படி பார்க்கும்போது 0 to 1 and union 3 comma 4 தான் E2 னுடைய inverse image. Okay, புரியும்னு நினைக்கிறேன். That is the idea. So the same way E3 னுடைய inverse image என்னது, f inverse of 3 comma 4. அப்படின்னா the collection of x belongs to 0 comma 4. f of x ன்றது 3 to 4 ஆ இருக்கணும். f of x is 3 less than equal to f of x less than 4. அப்படி பார்த்தீங்கன்னா function is defined 3 on this interval. எந்த இன்டர்வல்ல, 2 comma 3 இன்டர்வல்ல. ஓகே, so the function is defined 3 only on the interval 2 comma 3. 2 comma 3 ல மட்டும்தான் interval 3. Okay, so that E3 ன்றது that is called the 2 comma 3. அதே மாதிரி E4 ன்றது f inverse of 4 comma 5. So the f of x ன்றது 4 இல்ல 5, 4 to 5 இருக்கணும் அப்படின்னா that is called only possibility 1 comma 2. ஏன்னா function define பண்ணியிருக்கிறது, function f of x equal to 4 on this interval 1 comma 2. So இது எல்லாத்தையும் யூனியன் பண்ணி பாருங்க, E2 union E3 E4. So this is the union of the something. இது எல்லாத்தையும் யூனியன் பண்ணிங்கன்னா 0 comma 1 and 1 comma 2 and 2 comma 3 and 3 comma 4. So that is we get to the 0 comma 4. And what are the conditions? The measure is 0, intersection of the different set should be 0. So E2 intersection E3 ன்றது what is the E2 intersection E3? இது ரெண்டுத்துக்கு intersection எடுத்தீங்கன்னா இது 0,1 and இது 3,4. So that is 0, 1 and this is 3, this is 2 and 3 and 3,4. Clear? Okay. So that what is the intersection of this one? This is the intersection of 0,1, 3,4 and intersection with the 2,3. Intersection with the 2,3. So the no common elements, that is the intersection is the empty. Intersection is the empty. So the measure of empty set, that is the measure of empty set is 0. So that E2 intersection E4 is also that is empty set. E3 intersection E4 is also empty set. So the only the point so that is, but the measure is 0. Measure of the empty set is 0. Okay, so that each Ek is the union of the intervals and also measurable. Therefore the partition E2, E3, E4 is called the measurable partition of 0,4. That is the idea of the construction of measurable partition. And how to find the upper sum for that upper sum of the f over p and lower sum of f over p for this problem. So E2 ன்றது like that, இதான் E2 and capital M, that is called the upper sum வேணும், capital M வேணும். Capital M f over E2 is the supremum of the function. Supremum of the function 0,1 and 3,4 is called 2,2. ரெண்டுத்துக்குமே function வந்து 2 தான் இல்லையா? அதனால supremum of 2,2 is always 2 and small m ன்றது infimum of the function is also 2. Okay, infimum of the function is also 2. So measure of E2 is equivalent to measure of E2 என்ன வரும்? That is the measure of E2 means the length is 1, இதனுடைய length is 1, ரெண்டுத்தினுடைய union வந்து 1 plus 1, that is equal to 2. Okay, ஒரு இன்டர்வலுடைய மெஷர்ன்றது that is called the length தான். அதே மாதிரி E3ன்றது 2,3ங்க. capital M ன்றது that is called the supremum. Supremum of the function 2,3ல what is the function? 3. அதனால capital M ன்றது 3. Small m ன்றது is the infimum of the function in the interval 2,3. 2,3 that is equal to 3. And measure of E3, 3 minus 2, 1. Interval நுடைய measure ன்றது that is the length of the interval, that is called the 1. E4 ன்றது that is called the 1,2 and இது பார்த்தீங்கன்னா capital M ன்றது supremum of the function define பண்ணியிருக்கிறது இதுக்கு 4. அதனால capital M ன்றது 4, small m ன்றது is also 4. Measure ன்றது for this set E4 க்கு 1. So upper sum ன்றது capital M into measure of Ek. மொத்தம் 3 இன்டர்வல் வந்துரும். So measure of Ek ன்றது, so that is 2 into 2, 3 into 1 and 4 into 1, that is nothing but 11. Okay, so the same way lower sum how to define? Small m of f over Ek, so into m measure of Ek, that is 2 into 2, 3 into 1, 4 into 1, that is equal to 11. So upper sum equal to lower sum is both are equal. So upper sum equal to lower sum, when you use the theorem, f is Lebesgue integrable on 0,4. So the Lebesgue integrable integral 0 to 4 f equal to 11. That is the how to find out the Lebesgue integrable. That is the one of the important problem. Okay, and f is bounded measurable function. Bounded measurable function and C is lies between bounded measurable function means f is Lebesgue integrable. Am I correct? Already இப்போ தான் ரிசல்ட் பார்த்தோம். f is bounded measurable function னா f is Lebesgue integrable on a, b. If C is lies between the a and b, c ன்றது a வுக்கும் b க்கும் இடையில இருக்குன்னா f is Lebesgue integrable on a, c, f is Lebesgue integrable on c, c. இதே மாதிரி ரிசல்ட் நம்ம ரீமான் இன்டெகிரபிளையும் பார்த்துருப்போம். So that is the result. and f is the bounded measurable function on a comma b, and lambda is any real number. So the lambda f is also Lebesgue integrable. Lambda f is also Lebesgue integrable on a comma b. And f and g into the bounded measurable function on a comma b na, the f plus g is also bounded measurable function, that is Lebesgue integrable on a comma b. Okay, so bounded measurable function navi, that is called the Lebesgue integrable. Okay. That is f is bounded measurable function and g is a bounded function. F is bounded measurable function and bounded measurable function, and g is a bounded function. G is a bounded function on a comma b, and f of x equal to g of x almost everywhere. அப்படின்னா sum of the pointல இந்த ரெண்டு ஈக்குவலா இல்லைன்னு அர்த்தம். Sum of the point of the interval a comma b ல இது ரெண்டு ஈக்குவல் கிடையாது. So then g is a Lebesgue integrable on a comma b. F ன்றது is a Lebesgue integrable, but g is only the bounded function. But f of x equal to g of x இருக்கு almost everywhere, that is most of the point of the a comma b ல, then g is Lebesgue integrable ன்னு சொல்லலாம். That is the result. Okay, so f ன்றது Lebesgue integrable இருந்து f of x equal to g of x இருந்தாலே போதும், most of the point ல g is a Lebesgue integrable on a comma b. அதே மாதிரி f is bounded measurable function, that means f is Lebesgue integrable. f of x ன்றது greater than equal to 0 almost everywhere. Almost everywhere means that is most of the point is that f of x greater than equal to 0 is true ன்னு அர்த்தம். And integral a to b f ன்றது is greater than equal to 0. Okay, and f and g ன்றது both of them bounded measurable function. அப்படின்னா both of them Lebesgue integrable on a comma b. f of x less than or equal to g of x almost everywhere. So most of the point that is true. Integral a to b f ன்றது that is less than or equal to integral a to b g ன்னு சொல்லலாம். அதே மாதிரி f ன்றது bounded measurable function, that is the f is Lebesgue integrable, then mod f is also Lebesgue integrable. f ன்றது bounded measurable function இருந்தா போதும், mod f is also belongs to Lebesgue integral of a comma b. So modulus of integral a to b f ன்றது that is less than equal to integral a to b mod f ன்னு வரும். b less than a, so the integral a to b f to be minus of integral a to b f ன்னு சொல்லலாம். That is provided that f is integrable on b comma a, integral of that b comma a, the same idea இல்லையா? So that integral a to c, integral plus integral c to b ன்றது integral a to b define பண்ணலாம். And so now define integral e over the measurable set of f, that is f is bounded measurable function on a comma b, e is a measurable subset of a comma b. So the situation of the function f chi e will be bounded, f chi e will be bounded and measurable on a comma b, hence integrable on a comma b. So the chi e, that is the characteristic function of e, characteristic function of e. So that is very important idea in the Lebesgue integrable. So e is a measurable subset of a comma b, f into the bounded measurable function on a comma b, that is f is Lebesgue integrable. So then integral of the f over the measurable set e, not an interval, over the set e is defined as, how to define na, that is integral a to b f chi e அப்படின்னு define பண்ணலாம். The f chi e ன்றது is nothing but the bounded and measurable on a comma b. The integral e f then has the same elementary properties as those that just proved, that integral a to b f. Okay, so that is e1 e2 ன்றது disjoint measurable subset of a comma b அப்படின்னா, f is bounded measurable function on a comma b means then integral e1 union e2 f ன்றது integral e1 f integral e2 f. Just to use the definition we can prove. Okay, that is this is nothing but integral a to b f chi of e1 union e2. Chi is the characteristic function on defined on the e1 union e2. So from that we get it the integral another a to b f chi e1 plus integral a to b f chi e2, and then using the definition we get the result. So this is a very important result. In the case of E is the measurable subset of a comma b, f is bounded measurable function on a comma b, and lambda is any real number, then integral e lambda f equal to lambda times integral e f and சொல்லலாம். அதே மாதிரி E is the measurable f and g are bounded measurable function, integral e f plus g equal to integral e f plus integral e g. So this is another property, f and g are bounded measurable function, E is the measurable subset of a comma b, and f of x equal to g of x almost everywhere na integral e f equal to integral e g. E is a measurable subset of a comma b, f is bounded measurable function on a comma b na, then f of x greater than equal to 0. So முன்னாடி பார்த்த அத்தனை ப்ராப்பர்ட்டியும் இதில் வருது. Integral e over f greater than equal to 0. And the same way, so f and g as measurable, f of x less than or equal to g of x na, integral e f less than or equal to integral e g. So e is a measurable subset of a comma b, then integral 1 over e, that is equal to mesh of e, that is maybe e1. So that is the important. Integral 1 over e is nothing but the mesh of e, and f is a bounded measurable function on a comma b, f of x greater than or equal to 0 almost everywhere. So integral a to b f equal to 0, if integral a to b f equal to 0 na, then f of x equal to 0 almost everywhere. That is also very important. Okay, so that is the integral a to b f equal to 0 va irundaduna, f of x equal to 0 almost everywhere, a less than equal to x less than equal to b. So f is bounded and f is Lebesgue integrable on a comma b, then f is measurable. F is bounded and f is belongs to Lebesgue integral of a comma b, then f is measurable. So that is it's all very important. Okay, ஒரு ஃபங்க்ஷன் பவுண்டடாக இருந்து அது லெபெக் இன்டெகிரபிளாக இருந்ததுன்னா that function is called the measurable. Okay, so f is Lebesgue integrable on a comma b, e is the subset of a comma b, and with measure of e equal to 0, then integral e f integral of the f over e equal to 0. Okay, that is the problem. Okay, so f into the Lebesgue integrable, f is bounded and measurable. Am I correct? And capital M into the supremum, and capital M is the supremum of the mod f, that is called. So the consider the f chi e, that is means integral e f equal to integral of a to b f chi e. So the modulus of f chi e is less than or equal to capital M chi e, that is almost everywhere. That is called the mesh of e equal to 0 here, and chi e equal to 0 almost everywhere. So therefore f chi e equal to 0. So the almost everywhere. So therefore when you use it, integral chi e equal to 0, that is integral of the f over e equal to 0. Okay. The same way, then modulus of integral e f e less than or equal to integral e mod f, and integral m, that is capital M into mesh of e is 0, that is equal to 0. Okay. So integral f over e equal to 0. The same way, e1 e2 into the measurable subset of a comma b, f into the Lebesgue integral of a comma b, then integral of the f over e1, integral of f over e2 equal to integral of f e1 union e2, integral of f e1 intersection e2. Okay. That is the property. F is bounded measurable function on a comma b, and measurable function on a comma b, integral a to b f of x whole square dx. This is the f is Lebesgue integrable, that is integral a to b f of x whole square dx equal to 0. Then f of x equal to 0 almost x in a comma b. So that means g of x equal to f of x whole square, g of x equal to f of x whole square. We will try to prove integral g dx equal to 0. Okay, but then g of x, f of x equal to 0. Okay. Yes, so g is bounded, g of x equal to f of x whole square, g is bounded and measurable because of f is bounded and measurable, and also non-negative, that is a positive, it's a square because of real square. So integral a to b g equal to 0. Clear? So g of x into the greater than equal to 0. So integral a to b g equal to 0. So from this what is the conclusion? That is a g of x equal to 0 almost everywhere. So integral g of x is equal to 0 almost everywhere. F of x whole square equal to 0 almost everywhere. So that means which is implies f of x equal to 0 almost everywhere. That is of course. Okay. That is okay. And f be the bounded measurable function and f of x greater than equal to 0. So the f is Lebesgue integrable here. So f of x greater than equal to 0 almost everywhere in the a to b. E and f a measurable subset of a comma b, and with the condition E is the subset of f. So integral f over E is less than or equal to integral f over f. Okay. These are like the result. Okay. Using the E1, E2, En are the measurable subset of a comma b. Okay. And if each point of the 0, 1 belongs to at least 3 of this set, 3 of these sets, then at least one of the sets has measure greater than 3 by n. At least one of the sets has measured greater than 3 by n. That is the idea. So இங்க வந்து chi k, that is called with the characteristic function of E k in x is belongs to 0, 1, that is at least belongs to at least 3 of sets. The chi k of x equal to 1 has at least 3 values of k. For at least 3 values of k, that is a chi k of x equal to 1. That is summation chi k of x into the greater than equal to 3. Yeah. So when you integrate on both sides, that is integral 3 dx, that is called 3 over 0 to 1. So that is integral 0 to 1 chi k of x dx equal to mesh of E k. So this is the summation k equal to 1 to n mesh of E k is greater than equal to 3. So mesh of E k is less than 3 by n. Mesh of E k is less than 3 by n. If you take it, then mesh of summation mesh of E k n times 3 by n, that is equal to 3. This is the contradiction. So the mesh of E k should be greater than equal to 3 by n. Greater than equal to 3 by n. That is the idea. Okay. So இதுவரை பார்த்தது Lebesgue integrable for the bounded function. When you define for the Lebesgue integrable for the unbounded function. Lebesgue integrable for the unbounded function. So now extend the definition of the Lebesgue integral for the to the large class of the unbounded measurable function. Large class of the unbounded measurable function. Suppose f is a non-negative valued function. F is a non-negative valued function on a comma b. N is belongs to I. N is belongs to I. Define nf. இந்த suffixல மேல வந்து n போட்டுப்போம். So nf on a comma b. How to define? That is for each x in a comma b, let nf of x equal to f of x. F of x 0 to n ல எழுதலாம். F of x lies between the 0 to n னா n f of x equal to f of x. n f of x equal to n if f of x ன்றது greater than n இருந்தா, f of x ன்றது greater than n இருந்தா, that is called the n f of x greater than n. So that n f of x equal to minimum of f of x comma n. N f of x equal to minimum of f of x comma n. And so then a that is x is lies between the a to b. X is belongs to a to b. That is the idea. So the graph of nf is obtained by the truncating the graph of f. That is, for example, f of x equal to 1 by cube root of x for the 0 to 1. And f of 0 equal to 0. That means f of x equal to 0, x equal to 0 na f of x equal to 0. That is a function define பண்ணிருக்காங்க for the 0 to 1 க்கு define பண்ணிருக்கோம். So when you try to find out the 4f of x equal to, that is n f of x, that is the 1 by cube root of f of x. So by the definition, how to define, that is 1 by 64, 1 by 64, that means f of x, that is equal to 1 by 64 less than equal to x less than equal to 1, and 4 f of x equal to 4, that is equal to 4, that is called x lies between the 0 to 4, x lies between 0 to 4, and 4 f of 0 equal to 0. So by the definition, so this is the actual definition. So f of x is lies between the 0 to n, n under the 4 inga. Okay, so this is the definition. So then that is the x is lies between the f of x greater than n arundana, that is called that is equal to n, that is called the result. So the n f of x, that means 4 f of x, how to define, that is equal to 1 by cube root of x, correct, cube root of x, that is if f of x is lies between, that is f of x is cube root of x, 0 less than 1 by cube root of x less than or equal to 4. So when you simplify it, when you take the reciprocal, first of all, the reciprocal eduthingna, that is called cube root of x, that's equivalent to, okay, 0 strictly less than x less than equal to 4. So then cube root eduthingna, that is called the 64, 4 cube 64, 0 less than 1 by 3, 1 by x less than or equal to 64. So then 1 by 0 nu varum, infinity nu varum. So that is called infinity greater than x greater than 1 by 64. So that is 1 by 64 to infinity, but the function is defined for the 0 to 1 only. So that is nothing but 1 by 64, that is equality here. Inga equality irukku nenikiren, inga equality irukku. So that is the equality. So that is 1 by 64 less than or equal to x less than 1, that is 1 by cube root of x, that is defined. And the same way, 4th root of f of x equal to 4, that is n, f of x greater than n. So that means, so that is 4 f of x equal to 4. So then f of x is 1 by cube root of x greater than 4, correct? So when you cube on both sides, that is 64, and then take reciprocal, or then 1 by x greater than 64, when you take reciprocal, that is 64 less than, sorry, x is less than 1 by 64, x is less than 1 by 64, that's okay. N f of x, that is okay, n f of x equal to n, and n f of x equal to, for the a to b, when you define the minimum of f of x and n. So this is 1 by cube root of x, 1 by 64 to 1. How to get to the 0 to 4, that is 1 by 64. Something wrong. So I thought this is the 1 by 64. So 0 to 64. So 4th root of x, by the definition, this is equal to 1 by 64. Okay, so 4th root of f of x equal to 4 for the 0 less than x less than or equal to 1 by 64, and 4th root of f of 0 is always 0, f of 0 equal to 0 here. So that 4th root of f of 0 equal to, that is always 0. So when you define for the a to b, the minimum of f of x comma n, n f of x is the minimum of f of x comma n is called that n என்றது 4 இங்க. Okay, so 4 and f of x, which is the minimum for that a to b, that is called the n f of x. And f is a non-negative valued unbounded measurable function, and for each n belongs to I, the function nf is bounded function. So ஏன் இப்படி construct பண்றோம் அப்படின்னா, that convert into the bounded function. A non-negative valued unbounded measurable function, we want to change it to the bounded function, that is using the nf. That is a bounded function. Then f is measurable. Bounded function and measurable, bounded measurable function, that is called the, in the case of the nf is measurable. So the nf is measurable and bounded function of that is called the Lebesgue integral. Already நம்ம prove பண்ணிருக்கோம். So f is non-negative valued unbounded measurable function if limit n tends infinity integral a to b nf exists, then f is called the Lebesgue integrable on a comma b. F is called the Lebesgue integrable on a comma b. Define integral a to b f as integral a to b f limit n tends infinity integral a to b nf. That is very important. So then f is Lebesgue integrable, then right is f is belongs to L of a comma b. So in this example, f is function. So integral 0 to 1 nf equal to integral 1 by n cube to 1 by cube root of x dx plus integral 0 to 1 by n cube. That is a 0 to 1 under the, we can split it into like that, nf of x dx, because of function defined like that earlier. So this is the function for 1 by n cube to 1 க்கு 1 by cube root of x, அங்க 1 by 4 பார்த்தோம், 0 to 4 பார்த்தோம், that is okay 4 f of x பார்த்தோம். n வச்சு பார்க்கும்போது 1 by n cube to 1 1 by cube root of x, 0 to 1 by n cube, that is அங்க 1 by 4 வராது, 1 by 64 தான், that is 0 to 1 by n cube க்கு, that is called the n f of x dx. n into dx. So இது integrate பண்ணீங்கன்னா we get the result. Okay, so இது x power 1 by 3, that is called x power minus 1 by 3 னு வச்சுட்டு integrate பண்ணிட்டு limit போட்டிங்கன்னா we get this output. So இதில் limit n tends infinity போட்டிங்கன்னா, that is we get the 3 by 2. Limit n tends infinity 0 to 1 n f என்றது 3 by 2. So by the definition integral 0 to 1 f என்றது limit n tends infinity integral 0 to 1 nf, that is equivalent to 3 by 2. Okay, so this is equivalent to this one, so therefore this is equal to 3 by 2. This is one of the important problem. And f of x equal to 1 by x for the 0 to 1 and f of 0 equal to 19, then f is not integrable on 0 to 1. F is not integrable on 0 to 1. And f is, try பண்ணி பாருங்க, and f is non-negative valued measurable function on a comma b if f of x less than or equal to g of x and a comma b, and g is Lebesgue integrable, then f is also Lebesgue integrable. G is Lebesgue integrable na f is also Lebesgue integrable. Non-negative measurable function, the f of x less than or equal to g of x are the f is also Lebesgue integrable. அதே மாதிரி non-negative valued bounded measurable function on a comma b, then nf equal to f for all sufficiently large n, then integral a to b f equal to limit n tends infinity nf is also true for bounded f, and so f be the any real valued function, and define the f plus and f minus. Define the function f plus and the positive of the function, respectively the positive and negative part of the function. How to define the positive part of the function? That is the maximum of f comma 0 is called the positive part of the function. Negative part of the function is the maximum of minus f comma 0 is called the negative part of the function. That is also important concept. X belongs to a comma b, closed interval a comma b, f of x greater than 0, f of x greater than 0, and the positive part of the function is called the f of x, and the negative part of the function is 0 when you define like that. If f of x greater than 0 now, f of x less than 0 now, and then positive part of the function is 0, negative part of the function is minus f of x. If f of x equal to 0 now, positive part and negative part both of them equal to 0. Okay. So that is f is any real valued function on a comma b. F is any real valued function on a comma b, then f is defined as the difference of the positive and the negative part of the function. Okay, in the case of any real valued function, and mod f equal to sum of the positive and the negative part of the function. And f plus and f minus are non-negative valued, even though that is f minus is called the negative part of the f. And the graph f plus consists of those portions of the graph of f that is lie above the x-axis. And the graph of f minus is obtained by the similar fashion from the graph of minus f. For example, f of x equal to x square minus 1, which is defined the minus 2 to 2. And what is the positive part? Then the positive part of the function f of x equal to f of x, then minus 2 to minus 1, and the positive part of the function is 0 in the case of minus 1 to 1, and the positive part of the function f of x equal to f of x, then the x lies between the 1 to 2. The same way we can define the negative part for the minus 1 to 1, that is called the minus f of x. So the same way we can define. So the positive part means maximum of the function f of x comma 0. Okay. Negative part means maximum minus f comma 0. F enter the measurable function on a comma b. If both positive part and negative part are Lebesgue integrable, then we say that f is Lebesgue integrable on a comma b. So then our measurable function positive and negative part Lebesgue integrable on the function is Lebesgue integrable. And f is non-negative valued measurable function on a comma b is measurable subset of a comma b. For any n belongs to I, then n f chi e equal to n f of chi. Okay. So the integral e n f equal to integral a to b n f chi e. And f is Lebesgue integrable, then both sides of the 1 are not greater than 1, that is integral a to b not greater than integral a to b, so that as n tends infinity, limit each sides of the 1, then limit n tends infinity integral e n f equal to limit n tends infinity integral a to b n f chi. And limit n tends infinity integral e n f equal to integral a to b f chi. And E is any measurable subset of a comma b, and f is non-negative valued function in Lebesgue integral of a comma b. So integral f e equal to integral f e, that is equal to integral a to b f chi e. So this is equal to limit n tends infinity integral of n f. So f is an arbitrary measurable function in Lebesgue integral of a comma b. Integral f e as that is equal to positive part and minus of negative part, because of f equal to the difference of positive and negative part internal. And E is measurable subset of a comma b, and f is Lebesgue integral of a comma b, and G is Lebesgue integral of a comma b. F of x equal to g of x almost everywhere. Then integral g e equal to integral f over e. So So E1 E2 into the disjoint measurable subset of A comma B, then F is Lebesgue integral of A comma B, then integral E1 union E2 F equal to, that is already part of the same result. Yeah. So this is the log 1 by x. Okay, that is, I will try to find the 2f. So n f of x equal to, that is a minimum of f of x comma n. Okay, that is the definition. So f of x equal to log 1 by x, that is called log 1 minus log x, that is called the minus log x for the 0 to 1. So we want to try to find the 2f of x. 2f of x, that is a minimum of f of x comma n, that is minus log x comma 2. So that is minus log x less than or equal to 2. Okay, then log x greater than or equal to minus 2. So x is greater than or equal to e power minus 2, that is called the something. Minus log x greater than 2, na, x is less than log x less than minus 2, so x less than e power minus 2. So e power minus 2 node value approximately 0.13. That is the function. Now 2f of x is defined as minus log x. F minus log x nadadala minimum undradanaala. Okay, the minimum of the something. So 2f of x is minus log x. F in the case of x is greater than or equal to minus e power minus 2. Function is defined for 0 to 1. 0 to 1 ku define pannirukanga. E power minus 2 node value, this is approximately this one, something e power minus 2 less than or equal to x less than or equal to 1 and minus log x. Suppose this is equal to 2. Okay, so f 2 or that is called in the case of 0 less than x less than e power minus 2. X is less than e power minus 2 now, that is the minimum. Okay, x is greater than or equal to e power minus 2 something now, this is the minimum. That is the idea. So this is the answer. So 2f of x, minimum of the something, is the procedure. Okay, the same way we can define for this one 1 by x power p. Okay, if f of x equal to 1 by x power p 0 to 1, then f is Lebesgue integral on 0 comma 1 if p is less than 1, then integral 0 to 1 f equal to 1 by 1 minus p. Integral 0 to 1 f equal to 1 by 1 minus p. That is the f of x equal to x power minus p. This is the non-negative and measurable. Non-negative and measurable, and f is Lebesgue integral 0 comma 1. That is called n belongs to n. N f of x equal to the minimum of x power minus p and n. So x power minus p less than or equal to n, na? That is called x power minus p less than or equal to n. Then x is greater than or equal to n power minus 1 by p. X power minus p is greater than n, that is called x is less than or less than n power minus 1 by p. So then we can define like that. N f of x equal to mari define pannalam. So that is n power minus p x power minus p, and this is equal to n dx. இதை integrate பண்ணீங்கன்னா உங்களுக்கு output கிடைக்கும் இல்லையா? So இதை integrate பண்ணீங்கன்னா என்ன வரும்? That is n power minus 1 by p to 1. So that is equal to upper and lower limit, then x power minus 1 by p divided by 1 minus p. It's a very simple, minus p plus 1. So and then when you substitute the limit, we get this one. So the same way 0 to n power minus p, that is n power 1 minus 1 by p. So everything add panningna we get the sum output. And as n tends infinity in போடும்போது இதில் the n power negative, that is the denominator on anything by infinity 0. So this is also become the 0. So that we get the output as n tends infinity 1 minus leave it. This is 1 minus 1 by p. There is a minus of 1 minus p divided by p in போட்டுருக்காங்க. That is equal to minus of something. So இதில் n tends infinity போய் இந்த ரெண்டு portion 0 ஆயிடும். So we get the 1 by 1 minus p னு வந்துரும் answer. Okay. So this is the 0 to 1 n f of x. So that is, if p is less than 1, then 1 minus p is greater than 0. 1 minus p greater than 0 now, that is called, this is negative. In this case, this is approaches to 0 as n tends infinity. So then this is equal to 1 by 1 minus p. P equal to 1 ஆகுதுன்னா, that is called f of x equal to 1 by x. That is called 1 by 1 to 1. நீங்கள் இதிலே கூட substitute பண்ணலாம் outputலியே. So then this has become the infinity. The limit is diverges. In the case of p is greater than 1, this is less than 0. So minus of 1 minus p is greater than 0. So this is approaches to infinity. So then minus p by 1 minus p is greater than 0. Okay. So 1 minus p is less than 0. Then therefore this is equivalent to approaches to infinity. So limit is diverges. So f is Lebesgue interval on 0 comma 1 only in the case of p is less than 1. So integral 0 to 1 f into this is equivalent to 1 by 1 minus p. It's a very simple problem. So for understanding of the Lebesgue integral for the unbounded function. Okay. And f is a non-negative valued measurable function, and a comma b f of x less than or equal to g of x defined on the a to b. G into the Lebesgue integral on a comma b. F is Lebesgue integral on a comma b. Okay. It's also very simple proof. This is another problem. F of x equal to 1 by 2 plus sin x 0 to 2 pi. Then what is the positive part and negative part of the function? So positive part means maximum of the f comma 0. Negative part means maximum of minus f comma 0. If f of x greater than or equal to 0 nu eduthingina, 1 by 2 plus sin x greater than or equal to 0. That is sin x greater than or equal to minus 1 by 2. Sin x greater than or equal to minus 1 by 2 for x belongs to 0 comma 2 pi, except when sin x is less than minus 1 by 2. Okay. So that is called the inequality sin x less than minus 1 by 2. So that is called x is, that is true for x is belongs to 7 pi by 6 to ln pi by 6. Because of sin 7 pi by 6 and ln pi by 6, that is equivalent to minus 1 by 2. So for x is belongs to in this interval 0 to 7 pi by 6 and ln pi by 6 to 2 pi, the f of x is greater than or equal to 0. F of x is greater than or equal to 0. Okay. So f of x, positive part of the function is equal to f of x. Positive part of the function is equal to f of x in this part. Okay. Negative part of the function equal to 0. F of x is belongs to the interval now. The same way for x belongs to 7 pi by 6 to ln pi by 6, f of x less than 0. That is positive part of the function is 0 and the negative part of the function is called the minus f of x. That is called minus 1 by 2 minus sin x. This idea. Okay. இது ஒரு important positive part negative part என்றது என்னன்னு understand பண்ணிக்கிறதுக்காக. So f is measurable function on a comma b and mod f of x less than or equal to mod g of x. F is Lebesgue integrable on a comma b. And the f and g are in Lebesgue integrable na, fg is also Lebesgue integrable. That is true. The statement. It's a very simple proof. And f is non-negative real valued function, non-negative valued function in Lebesgue integrable. Then n equal to 0, 1, 2 and so on. En equal to x, n equal to x such that n less than or equal to f of x. less than equal to f of x less than n plus 1. So summation n times measure of En less than infinity. Okay. F of x equal to 0 for every x in the Cantor set K, for every x in the Cantor set K, and f of x equal to k for x in each of the intervals of the length 1 by 3 power k in k dash. Then f is Lebesgue integrable on 0, 1. Then f is Lebesgue integrable on 0, 1 and integral 0 to 1 f equal to 3. Okay, this is one of the problem. That is k is the Cantor set. Cantor set na it's 0, 1 interval over 1/3 of the interval delete பண்ணிட்டே போனீங்க. The collection of the set is called the Cantor set. And f of x equal to 0 for every x in the Cantor set K. And f of x equal to k for x in each of the intervals of the length 1 by 3 power k. Okay, in k dash. Then f is Lebesgue integrable on 0, 1. F is Lebesgue integrable on 0, 1. Okay, that is a 0 to f. That is Cantor k as measured 0 நமக்கு தெரியும். The complement of the Cantor set என்றது 0, 1 இருந்து Cantor set subtract பண்ணிடணும். அதான் complement. That is the union of the countably many disjoint open intervals removed during the construction of the Cantor set. At the kth stage, we remove the 2 power k minus 1 intervals, each of length 1 by 3 power k. Okay, the interval of the length 1 by 3 power k. So that is the removed at the kth stage. The Cantor construction stage 1 remove one interval, that is a 1 by 3, like that. Stage k remove 2 power k minus 1 intervals, each of the length 1 by 3 power k. So the function defined as எப்படினா 0 x belongs to k, k x belongs to an interval removed at the stage k. So then this f is measurable. So then since f is greater than equal to 0, therefore integral 0 to 1 summation k equal to 1 to infinity integral. So the kth stage interval f, that is called summation k, that is the into total length of the interval removed at the stage k, that is equal to total length at the stage k is 2 power k minus 1 into 1 by 3 power k. So இது simply பண்ணீங்கன்னா that is a k into 2 power k minus 1 into 3 power k. So then this is a form a geometry series, or that is k into something, that is 1 by 2 வெளியே எடுத்துட்டீங்கன்னா 2 by 3 whole power k னு வந்துரும். K times 2 by 3 whole power k. So 2 by 3 என்றது r னு வச்சுக்கோங்க, the k times r power k. So this is the geometry series like that. It's r by 1 minus r square, that is mod r is less than 1. That is r equal to 2 by 3 இங்க. So 2 by 3 something போட்டிங்கன்னா உங்களுக்கு you get the output 6. So integral 0 to 1 1 by 2 into 6, that is equal to 3. That is one of the problem. And f is Lebesgue integrable on a comma b and epsilon greater than 0, there exists a bounded measurable function g on a comma b such that integral a to b mod of f minus g is less than epsilon. Mod of f minus g is less than epsilon. Okay. And f is Lebesgue integrable for some c is belongs to real number, g of t equal to f of t minus c, a plus c less than equal to t less than equal to b plus c. That is g is belongs to Lebesgue integral of a plus c comma b plus c. So then a plus c to b plus c, g of t into the f of t minus c, that is called the integral a to b f of t dt k equal. So leave it. Where integral a to b f of t dt equal to integral minus b to minus a f of minus t dt. This is a well known idea. In the case of f is Lebesgue integral of a comma b. Lebesgue integral of a comma b. So like that result of A class simpler. And these are some fundamental theorems. That is f is Lebesgue integrable, and for the f is Lebesgue integrable now, that given epsilon greater than 0, there exists some delta, and modulus of integral f over e less than epsilon. E is the measurable subset of a comma b with measure of e less than delta. Measure of e less than delta. This is called the Lebesgue dominated convergence theorem. That is called the sequence of the fn be a mesh sequence of function in Lebesgue integrable a comma b. Limit the intensity fn of x equal to f of x. So that is the fn of x pointwise converges to f of x almost everywhere in the interval a to b. Suppose there exists g is belongs to Lebesgue integral of a comma b, then modulus of fn of x less than or equal to g of x almost everywhere. That is x is belongs to a to b, a comma b, and n is belongs to I. Then f is Lebesgue integrable. Then limit the intensity integral a to b fn equal to integral a to b f. So Lebesgue dominated convergence theorem of the sequence of function is the Lebesgue integrable, and the sequence of function converges to f of x, that is pointwise converges to f of x. The almost everywhere the point, that is almost the point, and some of the points this is not a pointwise convergence. And there is the g is another Lebesgue integrable function on a to b. The modulus of fn of x is always less than or equal to g of x. That is also almost everywhere, most of the point. Then limit n tends infinity, f is Lebesgue integrable on a comma b. Either on the pointwise convergence, Lebesgue integrable on a comma b, and the limit of the integral fn equal to integral a to b f. That is called the Lebesgue dominated convergence theorem. Pointwise convergence almost everywhere. Modulus of the sequence of function less than or equal to another Lebesgue integrable function, that is almost everywhere. Then f is Lebesgue integrable. That is the idea. That is called Lebesgue dominated convergence hypothesis use பண்ணீங்கன்னா Lebesgue dominated convergence theorத்தை இப்படி யூஸ் பண்ணலாம். And the conclusion, this is equivalent to this one. Okay, so limit n tends infinity integral a to b modulus of fn of x minus f of x dx equal to 0. That means integral a to b fn is converges to integral a to b f and f is Lebesgue integral. Okay, in case sequence of function, that is a sequence fn satisfy the hypothesis of the Lebesgue dominated convergence theorem, but doesn't converges uniformly. That is this is the example. Fn of x equal to root n, that is defined 1 by n less than or equal to x less than or equal to 2 by n, and fn of x equal to 0, otherwise that is 0 to 1 by n, 2 by n to 2 la the fn of x equal to 0. Sequence of function is 0. So the limit n tends infinity fn of x equal to 0 for the 0 to 2. Am I correct? And so satisfy the f equal to 0. Therefore, n for every n belongs to I, modulus of fn of x less than or equal to g of x. Okay, 0 to 2, where g of x equal to root 2 by root x. Root 2 by root x for the 0 to 2. Then g is Lebesgue integrable because of 0 to 2 x power minus 1 by 2 dx is the 2 root 2, that is the convergence, that is called the Lebesgue integrable. So the hypothesis of 2 is satisfied, and so that is it is the integral sequence of function satisfy the hypothesis of the Lebesgue dominated convergence theorem. So from this, in the sequence of function, that is f is Lebesgue integrable and then something. So but the sequence of function doesn't converges uniformly on 0, 2. Okay. So the Fato lemma means Fn is the sequence of non-negative valued function. And the example on okay, that is the root n, that is defined on the 1 by n to 2 by n. And Fn is the sequence of non-negative valued measurable function on a Lebesgue interval of a comma b, and the sequence of function is converges pointwise to f of x almost to the point on the a comma b. Then limit infimum of the sequence of function Fn is greater than or equal to integral a to bf if f is Lebesgue integrable on a comma b. The sequence of function would limit infimum is diverges to infinity if f is not a Lebesgue integrable of a comma b. Okay, well, that is the Fair's lemma. Okay, well, just a non-negative measurable function in a comma b, Lebesgue integral of a comma b sequence of function. As the pointwise converges to f of x almost everywhere are the limit infimum is greater than or equal to integral a to b f is Lebesgue integral of a comma b, and the f is not a Lebesgue integral of a comma b, the limit infimum, that is called the diverges to infinity. That is called the Fair's lemma. And f is Lebesgue integral of a comma b if capital F of x is defined integral a to x f of t dt na, and the derivative of the capital F of x is equal to f of x, that is also almost everywhere, most of the point. In the case of f is Lebesgue integrable, and this is f is belongs to Lebesgue integral of a comma b, and capital F of x defined as integral a to b f of t dt, and capital F is continuous on a comma b, capital F is continuous on a comma b. Okay. So how to prove the continuity? We want to choose the random point. The difference of the capital F of x, capital F of x naught is less than epsilon. Okay, like that, there is a convergence. That is less than epsilon, therefore continuous. And the sequence of function is sequence of function in Lebesgue integral of a comma b if mod of f1 of x is less than or equal to g of x, g is Lebesgue integrable, and the sequence of function is converges to f of x, pointwise converges to f of x almost to the point. H is any bounded measurable function on a comma b, then limit n tends to infinity integral a to b f and h is converges to integral a to b f h. Okay. Remember the sequence of function Lebesgue integrable in Lebesgue integral of a comma b, and this is the 0 less than or equal to f1 of x less than or equal to f2 of x less than or equal to fn of x and a to b, and suppose a sequence of fn of x converges pointwise converges to f of x if f is Lebesgue integrable of a comma b, limit n tends to infinity fn is equal to integral a to b f. That is also very important. And f is not a Lebesgue integrable, then integral a to b, the sequence of function is diverges to infinity. Okay. So this is called the monotone convergence theorem. Okay. The statement is very important. And f is Lebesgue integrable of a comma b, and for each n equal to 0 to 1 we can construct the En, that is the collection of x under the condition mod of f of x greater than or equal to n. Then summation of measure of En is converges. Summation of measure of En is the converges. So that means that is measure of En, how to construct the measure of Hn, measure of Hn plus 1 and so on, that is Hk equal to x collection of x such that k less than or equal to mod of f of x less than or equal to k plus 1. Okay. And then delta of measure of En, measure of En plus 1 measure of En, that is called the measure minus measure of Hn. Is that f of x equal to 2n, that is defined 1 by 2n to 1 by n. fn of x equal to fn of x equal to 0 for the otherwise 0 to 1 by 2n, 1 by n to 1. So actually the function is defined for the 0 to 1. So the integral 0 to 1 limit n tends to infinity fn of x dx, limit n tends to infinity integral 0 to 1 fn of x dx. So that is the Fatu's lemma apply பண்ணிருக்காங்க. So the result பார்த்தீங்கன்னா that is so that is for each x belongs to 0, 1 that large n, the 1 by n less than or equal to x less than x, fn of x equal to 0 and x equal to 0 and fn of 0 equal to 0, that is okay. And the limit n tends to infinity fn of x equal to 0 for x belongs to 0 to 1. So the limit n tends to infinity fn of x is 0, no? That is integral 0 to 1, this is equal to 0. And for the 0 to 1 fn of x, fn is the interval 1 by 2n to 1 by n. Okay, that is defined as 2n. The length of this one is 1 by 2n. On this interval, fn of x equal to 2n. So 1 by 2n to 1 by n, 2n dx. So the 2n into x limit போட்டீங்கன்னா that is equal to 1 by 2n, that value is 1. இல்லையா? So then limit n tends infinity, the something is 1. Okay. இதுவும் அந்த ரிசல்ட்டும் both are the different. So fn converges to 0 is the point wise. Lebesgue dominant convergence theorem apply பண்ண முடியாது. This is the consider the integral 1 to infinity x power minus p sin x dx. So the improper existence as an improper Riemann integral and as a Lebesgue integral depending on the p greater than 0. That is, if p is greater than 1, the integral exists in the both as an improper Riemann integral and as a Lebesgue integral. Okay, p is greater than 1 now. That is mod of x minus p modulus is something equal to less than or equal to x power minus p. So integral 1 to x power minus p dx is the converges for the p greater than 1. So this is the integral minus x power minus p sin x dx is converges absolutely for the improper Riemann integral, that is improper integral. Okay, one limit is infinity, sin infinity is oscillate. Okay, that is called the improper integral. So that u equal to x minus p direct integrate panna u equal to ud formula, then integrate infinity பதிலா a ன்னு கொடுத்தீங்கன்னா that is a is greater than 1. So this is the result 1 to a something. So a power minus p cos a is a converges to 0 as a tends to infinity. Okay, if since p is greater than 0, this is the x power minus p minus 1 less than or equal to minus x power minus p minus 1. So integral 1 to infinity x power p minus 1 is converges for the p greater than 0. So the second term is converges absolutely. This is the converges absolutely. So the improper Riemann integral is exist. For the Lebesgue integral பார்த்தீங்கன்னா that is the for the 1 to infinity. So that is x power minus p is less than or equal to x power minus p Lebesgue integral of 1 comma infinity since p is greater than 1. So x power minus p sin x is absolutely integrable in 0 1 comma infinity. So therefore it is exist as the Lebesgue integral. Okay. For the 0 to 1, the same thing. P lies between the 0 to 1. So each and every case we want to discuss, that is the integral 0 to 1 to a, the same type of integration, but as a tends to infinity, the p is inge vandu 1 to p is greater than 0, 0 to 1, that is called the p greater than 0, that is this is converges to 0, okay, and this is less than or equal to x power p minus 1, this is converges for p greater than 0. Therefore, the Riemann integral, improper Riemann integral exists, that is conditionally convergent, not absolutely convergent. So, therefore, failure of the Lebesgue integrability, that is called the integral 1 to t, modulus of something is converges. This is for the 0 to p to 0 less than p less than or equal to 1, this is not true. So, that is in equal to, when you construct the np plus pi by 4, npi plus 3 by 4, on in mod of sin x is greater than or equal to sin of pi by 4, that is called 1 by root 2, that is root 2 by 2. So, x belongs to in, x is less than or equal to n plus 1 into pi, that is x power minus p greater than or equal to n plus 1 into pi whole power p, that is equal to greater than or equal to something. Okay, so pi root 2 divided by 4 is something result. So, integral over the in x power minus p mod of sin x dx, that is greater than or equal to pi into root 2 pi power p n plus 1 whole power minus p. So, this is greater than or equal to summation of each and every interval, this is the output. So, n plus 1 whole power minus p is of order n power minus p. The series is the diverges for p less than or equal to 1. The interval for the 0 to 1 and so p less than or equal to 1, this is the diverges. So, therefore, this is the, by when you compare with the harmonic series, that is 1 by 1 pi n power minus p. So, therefore, the g of x is the root 2 for the x belongs to in, n greater than or equal to 1, 0 otherwise. So, therefore, mod of sin x. So, this is equal to diverges to plus infinity, therefore, this is the not a Lebesgue integrable on 1 comma infinity. Okay. So, little bit difficult. The same way sin x by x dx equal to for the 0 to infinity, that is called the pi by 4. The result of an approaching. So, this is equal to pi by 4, this is pi by 2, sin x by x is the proof on a paranga, if you understand, no problem. Okay. And sin square x by x square is also pi by 2. Direct result cake law, that is the proved by the previous result. Remember, sin power 4x by sin x square is also pi by 4. Just trigonometry identity use பண்ணி prove பண்ணிருப்பாங்க. That is pi by 3. So, this is the a greater than 1 is fixed. Consider the integral x power p log x whole power q dx integral a to b, p comma q belongs to r. This integral is exists as an improper integral and as also the Lebesgue integrable. If in the case of the p is less than minus 1 or p is equal to minus 1 or q is less than minus 1. Okay. So, like that. Sine square, this is the improper integral. Integral 0 to 1 to infinity already discussed பண்ணிருக்கோம். So 1 to infinity sine square 1 by x and x power p e power minus x dx. So this is the integral, the improper integral is exist and Lebesgue integral ஆகும் this is the exist. So prove பண்ணிருக்கோம். This is another problem. The problem கொஞ்சம் பாருங்க. This is how to prove that in the Riemann integral and Lebesgue integral, that means improper integral and Lebesgue integral, how to prove this one. Let the combine many problems and improper and Riemann integrals, improper and Lebesgue integrals. These are some problems. Okay. So these are at least in the summary table and the problem வந்து இதெல்லாம் improper integral exist ஆகும், இதெல்லாம் Lebesgue integral exist ஆகும்ன்றது the integral problems. Okay. அதே மாதிரி this is another problem. So Lebesgue integral exist ஆகிறது what are the condition அப்படின்றது. Only Lebesgue integral exists for this problem, that is called p is greater than minus 1 and q is greater than minus 1, that is near x equal to 0, that is and x equal to 1. So x equal to 0 that is 1 by x square whole power q, that is approaches to 1. So the integrand is approaches to x power p, that is integral 0 to epsilon. ஏன்னா 1ன்றது here, okay, so 0 to epsilon x power p dx. So that is the converges only in the case of p is greater than minus 1, depend on the p. X equal to 0 ன்னு எடுத்தீங்கன்னா near x equal to 0 and near x equal to 1, t equal to 1 minus x ன்னு எடுத்துட்டு, that is called t is approaches to 0 plus, that is 1 minus x square, that is approaches to 2t, that is called the 2t whole power q ன்னு வந்துரும், that is x power p approaches to 1 ன்னு வந்துரும். So the 2 power q and t power q, that is 0 to eta, t power q dt is converges q is greater than minus 1. So when you conclude the both of them, p less than minus 1 and q is greater than minus 1 la, this is the Lebesgue integral. Problems are there. So the condition of the table பண்ணிட்டு எல்லா ப்ராப்ளத்தினுடைய ஒரு கன்க்ளூஷன். எந்த கண்டிஷனில் Lebesgue integral is exist. So most of the problem கேட்கலாம், not only TRB exam, the CSIR NET exam. Stop here. முடிஞ்ச அளவுக்கு பாருங்க. ஓகே.